Jiesong Liu is an undergraduate at Renmin University in China. His research interest lies in the fields of computer architecture, design, compiler optimization, programming systems, and acceleration for programming languages and machine learning. Today he's going to talk a bit about his AI machine learning method, space-efficient TREC for enabling deep learning on microcontrollers.
Thank you, Trevor. Hi, everyone. My name is Jiesong, and I'm a senior student in Renmin University of China. I'm going to go through my work of space-efficient TREC for enabling deep learning on microcontrollers. So I'll introduce the motivation, the work itself, some of the experiments we conducted, and how they actually turned out. So in the past years, AI and deep learning applications often run on the cloud, taking the form where the data are collected on the edge and streamed to the cloud through a network and processed remotely. However, there are increasing demands for running machine learning applications right at the edge where the data are generated, and now to the microcontroller-based devices. So microcontrollers are a dominating computing engine market for its small, low-cost, and energy-efficient devices. They exist everywhere, from household appliances to cars, consumer electronics, wearables, and so on. It is estimated that over 250 billion microcontrollers are already in use right now. So microcontrollers are very resource constrained. For example, the STEM32F469i microcontroller contains only 324 kilobytes SRAM and 2 megabytes flash on-chip memory. So as a result, they have been widely regarded viable only for simple applications such as keyword spottings rather than complex DNA models. But enabling deep learning on microcontrollers brings huge benefits for us. So first, we don't send data back and forth, which is good for bandwidth and energy, and thus avoid network congestion issues as well. More importantly, the transfer latency is totally eliminated, bringing better prediction performance. So, and finally, since all user data are processed locally, this design eliminates many privacy concerns as well. So this figure shows a use case of anomaly detection on the microcontrollers, which we apply microcontroller on a server model to retrieve vibration data. And the anomalies can be detected and reported in real time. In this particular case, the detection latency of over 1 second is improved to 317 milliseconds when DNNs are moved from cloud to the device end. So in the same case, many other tasks can benefit from on-device AI, ranging from exoskeletons to voice activations, object detections, and so forth. But there exist some challenges for enabling deep learnings on microcontrollers. First, DNN models are really computation intensive. And second, edge devices are usually resource constrained, just as what we've covered. So therefore, eliminating computation redundancy becomes a practical approach. So depending on where the redundancy comes from, redundancy in DNNs can be classified into lasting and transient redundancy. Lasting redundancy rises from DNN parameters. It can be detected and removed through methods such as pruning and quantization, while transient redundancy comes from input data or activation maps. It has to be detected and removed in every inference. Several studies have explored similarities in input for DNN accelerations to remove the transient redundancies. Deep reuse is a pure software approach. It actually inspired this current work. It incorporates a randomized clustering components and thus suffers from accuracy fluctuations. deep reuse uses several hashing vectors, so it actually increases the space usage. And in reference to the locality-sensitive hashing, for a parameter vector v, the input vector x is transformed into 1 or 0 through the following hashing function. So in our work, we propose a new approach, space-efficient TREC, to substantially improve the state-of-the-art of DNNs on microcontrollers. TREC stands for Transient Redundancy Elimination-Based Convolution. Its key idea is to identify similar elements in the input data of the convolutional layer and avoid repeating similar computations on the fly. So in the right figure, to compute the convolutional layer, the common practice is to unfold the input images and filters into input matrices X and the weight matrix W, and then perform the general matrix multiplication with these two matrices. The key idea behind is that strong similarities exist among neural vectors. Here, a neural vector is composed of several consecutive elements in the role of the unfolded input matrix X. Therefore, the neural vectors can be clustered into small number of groups, and the computation results from the cluster centroids of each cluster can be reused by all the neural vectors in the same cluster. By incorporating this novel TREC operator into our system, both in the forward and backward paths, we successfully group similar neural vectors into the cluster to detect and remove redundant computations. However, TREC does not consider space efficiency. Actually, it increases the space usage substantially due to the extra space needed to store the hashing vectors and the cluster indices. And this actually brings huge heavy burden for the device in terms of the space usage. So to achieve space efficiency, we deployed a method called kernel reuse. The key idea is to implement hashing in a space-efficient way by reusing parts of the matrix that is already part of the DNN computation as the collection of vectors required to implement clustering. So in a sense, vectors making up this matrix thus serve the double duty as hashing vectors and matrix elements at the same time. And this technique actually avoids huge memory overheads in practice and achieves high speedups on real DNN computations. So as for the experiments, we use 3 different platforms, and one is the robust machine as a server for training and 2 low-end microcontroller devices for inference. We evaluate our solution by applying it to 3 popular DNN networks. They are CipherNet, ZFNet, and SqueezeNet. And we conduct experiments on 2 microcontroller models. One is for STEM32F4 series, and one is categorized in STEM32F7 series. And we can, in this table, we can see that by implementing our solution on microcontrollers, we're able to avoid over 69% of computations on convolutional layers in theory, and actually we achieve an average of 3 to 5x reduction in the overall network latency with no or marginal accuracy loss. Actually, compared to the conventional DNNs, we have better speedups, and compared with the deep reuse method that inspired our work, we have better accuracy performance. Actually, in fact, it's the more stable accuracy performance. Besides, it can be a plug-and-play replacement for convolutional layers in mainstream DNNs without additional efforts. It is also orthogonal to lasting redundancy eliminations methods such as quantizations and model pruning, which actually is used in our work. So all of these techniques can be combined for the better results. So in conclusion, in this work, we demonstrate that large DNNs can be deployed on resource-constrained microcontrollers and executed efficiently by the introduction of space-efficient TREC. It takes advantage of computation, reduction, and space savings. And it maximizes performance and obtains stable accuracy results. This is all for the presentation. Special thanks to the great efforts and help from Dr. Shen and Dr. Zhang. Thank you everyone for listening, and don't hesitate to reach out to me. Thank you.